Okay, there's a lot of detail in this chart, and I enlarged it as a result. An example from your book, and it's a combination of friction and force. And the scenario is, imagine a car, first of all, going up a hill, inclined at angle theta, and braking, in which case the motion diagram would be as you see here, and the a sub x would be down the slope. Or a car coming down the hill and braking, in which case the motion diagram would be ever shorter displacement vectors going down the hill, which means j sub x is up the hill. And then thirdly, imagine that same car always keeping the initial velocity the same and using the same coefficient of friction is going on a level surface and braking. And so the question posed is to find the stopping distance in each of these three cases. And so what I did is I did the level one first. And so for the level one, there are three forces acting on the car. I'm going to use a coordinate system. It's a standard one, y up and x to the right. The initial velocity of the car is assumed to be 30 meters per second. This isn't going to kick in yet, but the angle of the slope when we get to these two cases is 10 degrees. The mass of the car is 1,500 kgs. And the kinetic friction, which is appropriate here because the car is moving in all these three scenarios while it's stopping, is rubber on road, which is 0.8. So for the level scenario, we have an x component of the Newton number 2, which says that F minus F sub k, that's the frictional kinetic force, is equal to the mass of the car times the acceleration in the x direction. The y equation says that n equals mg, and so putting these two things together, I can conclude that F sub k is uk times n, which is mu k times mg. There should be a minus sign here. So a sub x is, from this equation, is minus f sub k over m, which is minus mu sub k mg over m. The m's cancel, it's independent of mass. And so the acceleration in the x direction is minus mu k times g. In other words, it's minus 0.8 times 9.8, which is 7.84 negative meters per second. And now one can use equation number 3, constant acceleration, to compute the displacement the car undergoes while stopping. And again, we see this pattern of negative on the bottom, negative on the top, giving me a positive displacement. Turns out to be 57.4. All right, so now let's go up the hill. If I go up the hill now, I'm going to tilt my coordinate system. As you see here, I'm going to have the coordinate system point up the hill. The x direction points up the hill. The y is up and perpendicular to the ramp. And so I have the same three forces here, but what I'm going to do now is n is perpendicular to the ramp, and so it's in the direction of y. F sub k is in the direction of minus x. F sub g, however, is neither parallel nor perpendicular to the ramp, so I break it up into components which are either parallel, that's the mg sine theta, or perpendicular, that's the mg cosine theta components. And so if I write the x component of Newton number 2, looking up here, looking at the direction for the positive x-axis, it's going to be minus mg sine theta, that's this guy, minus f sub k, that's that guy. They're both pointing in the same direction and anti-parallel to the positive direction for x, is equal to ma sub x. And for the y direction, I'm going to conclude that n is equal to mg cosine theta. So now I can put a story together for f sub k. F sub k is mu sub k times n, which is mu sub k times mg cosine theta. And so x now, if I put the expression for f sub k in from here to here, I get minus mg sine theta minus mu k. Mg cosine theta is equal to m times a sub x. The m's cancel, and I get an expression for a sub x, which is minus g times the sine theta plus cosine theta times mu sub k. If I plug in the numbers, 10 degrees for theta, 0.8 for mu sub k, I get an a sub x of minus 9.42 meters per second per second. Again, the negative meaning that it is pointing down the slope in the negative x direction. Equation number 3 from our kinematic set then allows me to compute 47.8 meters. Okay, so the stopping distance is less if the car is going uphill and braking than it is going on the level. And so why is that so? Because we have an extra mg sine theta braking force in addition to the s sub k. Now, on the other hand, if the car is going downhill and braking, now the friction is one way and the mg sine theta is the other way. So the x component equation is minus mg sine theta plus s sub k is equal to m times a sub x. I have to keep this as a positive number because it's pointing in the positive direction. And my y equation again gives me n equals mg cosine theta. So f sub k is in magnitude the same. The direction is different. Mu sub k times mg cosine theta. So my x component equation now becomes minus mg sine theta plus mu sub k mg cosine theta equals m times a sub x. So the m's cancel as they did before, and now we get an a sub x equation, which is g times mu sub k cosine theta minus sine theta, which is 6.02 up the slope, and the stopping distance is now 74.8. This is the longest one with the car going downhill and braking. Okay, so one neat thing about all of this is underneath here and over on the side, I do a general calculation where I leave theta open. Theta can be plus if we're going uphill. Theta can be minus if we're going downhill, or theta can be 0 if we're on the slope. We should be able to have one equation that does all three cases. So delta x is equal to v x naught squared divided by 2g sine theta plus mu sub k times cosine theta. Now if I put theta equals 10, mu sub k equals 0.8, v naught x equal to 30 meters per second, I get 47.8 meters, which is what I got before. If I'm going down the hill and I put theta is equal to minus 10 degrees, well, okay, so cosine of minus 10 is the same as cosine of 10, but the sine of minus 10 is minus the sine of 10, and so you get the component of the gravitational of the weight parallel to the slope, and the frictional force either fighting each other or not fighting each other. And in this middle case here, these two things are fighting each other, and you get a larger stopping distance as a result, because of the negative angle and because now you have these two terms partly canceling each other. And then finally, when you go over to the level case, simply putting theta equals 0 in here makes this term disappear, and I get the same expression I got up above here, if you look, and the same stopping distance is computed. So I did this problem two different ways. I did it one case at a time, and then I did it with a formula that I showed I could apply to each one, using different values of theta, plus 10 for the first, minus 10 for the second, and 0 for the third, obtaining the same numbers that I had previously gotten.